Hi everyone, and welcome to this lesson of GPT in a nutshell, where I'm basically going to try and make you understand exactly how GPT models work by understanding their underlying architecture, which is transformers. So usually you would need a master's degree or years of studying to try and understand these. So I'm going to try and attempt to teach you a summary of this in just one quick video. Let's go. So for years, scientists have been trying to model the human brain. And the reason for that is because if we are able to model the human brain in a digital form, we'll be able to process complex data, such as language or images or video, or even sound and music and stuff like that. So for years, they've been trying to develop what you call artificial intelligence so that you are able to solve these more complex problems. So a human brain kind of looks like this, where you have a whole lot of neurons in these yellow dots, and then they're all connected by synapses, which transfer information from one neuron to another. So they were able to digitize this with something called an artificial neural network, also referred to as an ANN, which basically has all these nodes, which represent neurons, and those synapses are represented by these weighted edges, which basically contain a number or a parameter value. So as you can see here, the blue, the darker the blue, the more negative the number, and the more red, the more positive the number. So it starts off with an input layer, and that is basically these nodes are receiving information from the outside world. All right, so that's like, call it input data. And then it passes through a whole lot of hidden layers, right? In this case, this ANN has 2 hidden layers, and then it gets passed to the output layer, which is usually something like a prediction. So with this specific model, you're able to solve a whole lot of complex problems, and a whole field of study emerged from this called deep learning. And it's called deep learning because the same way the human mind learns from its surroundings, these models also learn. So this process of assigning weights or parameters between all these different nodes is called learning. And with learning, you are able to build more intelligent models. The larger the base model size, the larger the memory. So if we look at these examples of different language models, we have GPT-1, which was developed back in 2018. Then we have GPT-2, which was more intelligent, GPT-3, which was even more intelligent, and GPT-4, which is even more intelligent. And the intelligence of these models are directly proportional to the amount of parameters or those weighted connections between the nodes. So the more of those parameters that you have, the larger the model, and as a result, it's able to learn more and it performs much better and it can solve much more complicated tasks. So we can see back GPT-1 was a tiny little dot, only had 117 million parameters. GPT-2 had 1.5 billion. GPT-3 had 175 billion. Then GPT-4, according to a few resources online, I found that it has 175 trillion parameters. Don't quote me on that because OpenAI haven't publicly said how many parameters it was trained on, but this is what they estimate and experts estimate online. So how do these large language models get trained? How do they actually learn? All right. So in this case of a large language model, it's trained on a whole lot of input data. And this input data is literally just text in raw format gathered from resources like the internet, like Wikipedia or books. And they take all that text and it basically trains on that data. And this is how it works. So it'll take the input training as data. For example, let's say one sentence in that massive corpus of text said something like, once upon a time in a land far, far away, blah, blah, blah. What it then does, the model is set with initial random parameters. So remember we saw over here, there's like 117 million or 175 trillion parameters. So this would go on to like 4 trillions of different parameters, and they're all randomly initialized. In this case, they're all just set to 1. Okay. Then what the model does is it tries to guess the next word. Okay. Because remember how these neural networks work. It tries to predict an outcome by going through all those hidden layers, and it tries to make a prediction. So it'll take, say, for example, the word once, and it then needs to predict the next word. So let's say, for example, the model then predicts the next word that comes after once is the word there. All right, here's the word there. Then what the model does is it tries to calculate the difference between the word that it predicted and the word that it should have predicted based on the training data. So what I have here in step 4, it calculates a difference between the predicted word there and the actual word in the training data upon. So if we look at the training data, it says once upon. All right. So it predicted there, but it should have been upon. So what it does is it tries to calculate the difference mathematically. It's able to quantify these words using math, and it tries to minimize what they call a loss function. So don't worry too much about how that actually works, but basically they're trying to calculate the difference between what was predicted and what should have been predicted based on the next word. And what it then does is it auto adjusts the parameters. So for example, in this case, it adjusted parameter number 3 to 12 and parameter 6 to -5. Now, as a human, these parameters, we aren't able to interpret them, but the model, by adjusting these parameters, will now, the next time it tries to predict what word comes after the word once, it'll have a higher probability of choosing the word upon as opposed to choosing the word there, because these parameters have now been adjusted. Now, as it runs through these more and more training data and adjusts more and more of these parameters, these models get smarter and become better at predicting what the next word should be based on the training data. All right, so GPT stands for Generative Pre-trained Transformer. So the generative part means that it refers to generative AI, which involves creating or generating new content. For example, generating text, generating images, generating videos, generating music, etc. Then we have pre-trained, and pre-trained means the model was previously trained on data. And then lastly, we have transformer, and this refers to the model's architecture called a transformer. And this is what a transformer looks like. All right, this is just a diagram of what it looks like internally. And this was the biggest breakthrough of what made ChatGPT possible. This was developed in a scientific research paper called Attention is All You Need from 2017. And from that research paper, GPT-1 was then developed in 2018. And then ever since then, these models have just been getting better and better. The same transformer architecture is what Google use in their AI called Bard. Theirs is called Palm. Instead of GPT, they use Palm, but it's also based on the transformer architecture. So this transformer architecture sits between two layers called tokenization and de-tokenization. And I'm going to explain every step through this whole process, and it's quite interesting to actually understand how these models work internally. So the first step is tokenization. So what is that? Tokenization is converting words to numbers, all right, also referred to as token IDs. Because remember, these are mathematical models. So in order to understand these words, you convert those words into numbers, which are much easier to process. So this is what tokenization looks like. You get something called a tokenizer, which converts text fragments into token IDs. And if you want to experiment with a tokenizer, you can go to platform.openai.com/tokenizer. That's where I got this screenshot from. And what it does is it uses what you call a tokenizer dictionary to correspond the words or tokens to numbers, which is token IDs. So this is what the dictionary would look like. Okay. And we'd have every single word, and this goes on for about 1 trillion. There's no reference to how many tokens there are in OpenAI's tokenizer dictionary or GPT tokenizer dictionary, but there's billions, if not trillions of them. So for example, the word the with a lowercase t, because this is all case sensitive, refers to token ID 1169, and that's static. The letter A, lowercase, refers to the number 64. The word and is 322. The word hello with a capital H is 15,492, etc. All right, so then when these models take text as input, for example, the fisherman caught the fish with a net. What it does is it then converts this text into an array of token IDs. So it'll take the and assign it to 464. Notice it's a capital T, so that's why it's not this number. The with a capital T is 464, and that's where it gets the value from. Then the word fisherman, and it's that number. Then the word caught, the fish with the net. Even full stop over here references token ID number 13. Now that's tokenization. We've now gone through the step from converting the words into token IDs or numbers. The next step is to convert these token IDs into what you call a vector, okay? And that is done in this embedding stage over here, okay? So a token embedding is a high-dimensional space where each token is mapped to a unique position called a vector. So when I say high-dimensional, as a human, we're only able to visualize 3 dimensions, all right? Maximum 3 dimensions. We can visualize 2 dimensions, and we can even visualize 3 dimensions. In this case, we have a Z dimension, X dimension, and Y dimension. Just like real life, we look around, everything's in 3 dimensions. So this is just a diagram to represent what a token embedding would look like, but in reality, there's a lot more. There's a few hundred dimensions. So in this space, each token ID is mapped to a position in space, and these are also predetermined, just like the tokenizer dictionary. This high-dimensional space is a static space where every token exists somewhere in space, all right? And that's how you're able to quantify a word to a number. So if we look at the word fish and fisherman, because they both have to do with fish, they're quite similar. So in the embedding space, they're quite close to each other. The word net is also kind of close to fish and fisherman. It's a little bit further away, but usually you can catch fish with a net, so that's why they might be close to each other. And then you might have the word ball, which maybe doesn't have anything to do with fish and fisherman, so it's a little bit further away. But the word ball and court can be closer together, or the word court and fisherman are also kind of close together because you can catch fish. Then you have things like sound. Now, sound is very far away from maybe the word net, but it's close to the word ball, because balls make a sound, possibly if you kick it or something like that. So basically, all these words represent a position in space relative to every other word, and the closer they are, the higher semantic similarity they have with each other. All right, so here I have an example with the word fish, and in this specific example, the coordinate of the fish in the X, Y, and Z plane is 12.5, so whatever unit that is, let's say 12.5 meters, all right? It's not actually meters, but let's say 12.5 meters. And then Y is 9.4 meters, and then Z is 3.2 meters high. And that's the position in space that it represents. But remember, like I said, it's a high dimensional space. So for example, in the attention is all you need paper, they use 512 dimensions. And I know ChatGPT, they use a much larger amount of dimensions in the embedding space. All right, so that is how you're able to mathematically understand language. You're able to calculate the distance between 2 vectors using the sum of the absolute difference between elements at position I in each vector. So let me demonstrate an example of this. Let's take the word cat and dog, all right? And this is what the vector looks like. Let's assume there's 512 dimensions. So instead of just having 3, 1, 2, 3 like we had before, this carries on, comma, another number, comma, another number, comma, and this carries on for 512 dimensions. Now, what you can do is you can subtract 2 vectors, one vector minus another vector. You'll be able to quantify the distance between those 2 vectors, and then you'll be able to know how similar or how different those words are. So for example, if you take the word cat and dog, because they're both domestic pets, they'll probably be quite similar to each other, quite close to each other in the vector embedding space. So the way you'd calculate that, you'd take 1.5 minus 1.7, and then you'd say plus, you'd say minus 0.4 plus, minus 0.3 plus 7.2 minus 6.9 plus 19.6, etc., right? So what would happen is, because these numbers are quite similar and you sum all these numbers together, that number is not going to be too large because they're quite close together. Whereas if you try to calculate the distance between the word cat and PS4 remote, because they're quite different things, you can see even just by looking at these numbers, they're much higher numbers as opposed to these. They're much different. So because of that, the distance between those 2 points in space are going to be much higher. And that is how you mathematically are able to understand language. So now that we have embeddings, we can then use those embeddings to calculate the position of every token in the sequence of tokens. So this is what you call positional embeddings. So that PE over here stands for positional embedding. And this is what it looks like. So positional embeddings, there's a vector for every single token. And this is calculated with some fancy calculations using sine and cosine. And what this basically represents is the position of each word in a prompt relative to all the other words. So this way it's able to understand context. So this is why these GPT models are so good at understanding language, because in language, the order of the words are very important in order to translate it. If you try to translate English into Greek, you can't just translate the first word or translate each word and then just linearly translate each word, because the grammar won't make sense. So with understanding the position of each word, it's able to actually translate it much better. And that's why if you think back in the day with Google Translate wasn't really good at translating languages, because it was kind of translating each word sequentially and it didn't understand grammar, or not just grammar, just in general word order for different languages. Whereas with positional embeddings, it made that possible. So what the model then does, it takes the token embedding, which we learned, which is a position in space of that token ID, and it adds it with a positional embedding. All right. So you're basically summing two vectors together, and then you get this final input embedding over here. All right. So this vector basically just represents a position in space that contains both the information of what the token means, the definition, for example, the word net, that's a token embedding, and then the positional embedding, it also represents that, which is where the word net is relative to the other words in the prompt or in the input text. So this was quite a big breakthrough, these positional embeddings, because like I said, it allowed the model to understand the position of words relative to other words in an input. It then takes those final embeddings and it gets fed into what you call the self-attention layer, all right, inside the encoder and decoder. And what this self-attention does is it assigns weights to every word relative to every other word. So let me show you what that looks like. So let's take, for example, the sentence, the fisherman caught the fish with a net. Let's say this is the prompt, okay? It's not really a question, but let's just assume it's a prompt. What it does is it assigns parameters. Remember what I showed you earlier with the neural network, where those lines in between the different nodes are assigned different weights? You also call those weights parameters. It's just a synonym. So between each token and every other token. So you can see it will assign maybe a light line between the and the word the, but a thicker line between the word the and the word fisherman, because it's basically saying there's a strong importance between the word the and fisherman. So now the model knows the thing that the article the is referring to the noun fisherman. And then it assigns another weight between the and caught, which is a bit thinner. It's not as important as fisherman, and so on. And then it assigns all these weights. Now, it doesn't just do that with the first word. It does that with every single word relative to every single other word in the entire prompt. Okay? And then what you get is you get this net of all these parameters between every word in a prompt relative to every other word. And these are all weights and numbers. Okay? And with that, you are able to understand the importance of the context of what the prompt is saying. And now it doesn't just do this once, it does this multiple different times. And that's why it's called multi-headed self-attention. If we look here, remember the self-attention layer had multiple different layers, and that's because it's multi-headed. And by multi-headed, what I mean is that each self-attention head, so this is one self-attention head, this is another self-attention head, etc. And usually there'll be somewhere of a range of 12 to 100 of these self-attention heads, and each one represents something different. For example, in this one, the parameters or these weights might be based on the people relationships between the different words. This head might be based on the activities that are performed. This one might be based on words that rhyme. So words that rhyme might have a higher or a thicker line or a higher parameter value between them. And others may not be as easy to interpret. So that's something important to note. These different self-attention heads aren't something that the developers pre-programmed beforehand. The AI basically just creates these different self-attention heads that represent different things in the neural network. So it's usually quite difficult to actually analyze these different self-attention heads and figure out what they mean. The next step, step 5, is it predicts the next word by assigning scores for each word. So that's how these models work. As I mentioned earlier, the same way how the models get trained, it tries to predict the next word. That's how it basically runs. I'm sure you've seen when you run a GPT model and you click submit, it starts generating one word at a time. That's because it's busy predicting the next word as it goes. So this is done in the feed-forward network. So this feed-forward network, it takes all of the attention weights as input from the previous step. And then what it does, it makes a prediction for what it thinks the next word could be based on its training data. And it does this for every possible word it knows in its vocabulary, which is that token dictionary that I showed you earlier. So these predictions are not probabilities yet. They're just scores, or what they call logits. And these scores together form a vector of logits. Right, now, all these scores, it's basically just numbers, and they're in proportion to the probability of which word should be chosen next. So in simple terms, a vector of logits is a list of scores that the model gives to each possible next word in a sentence. So for example, if the model is trying to predict the next word in the sentence, the cat is, the vector of logits is an array like this. For example, it'll open square bracket 2.3, 4.97, 3,584.21, etc. And this carries on for all the trillions or however many tokens there are in the tokenizer dictionary. And what it would do, it might give a high score to the token, for example, sleeping, a medium score to the token running, and a low score to the token apple, etc. And this because that's a word that would come after the phrase the cat is. So it's more likely that the cat is sleeping as opposed to the cat is apple. So these scores are then called logits. What then happens, those logits or scores get fed into what you call the softmax output, and it converts those scores into probabilities. So the model then turns these scores into probabilities between 0 and 1 using a mathematical function called softmax, so that they all add up to 1. So for example, this is what the vector would look like, and all these numbers, instead of being scores, are now a probability of likelihood of what the next word should be. This gives a probability distribution over all possible next words, and the word with the highest probability is chosen as the prediction. Once we've got that vector of probabilities, that vector of probability then gets converted to token IDs or words. All right, so that's what you call de-tokenization. It's the opposite of tokenization, where it takes the token ID and it converts it back into a word. So how does it do this? If we look at the probability vector as we had in the previous case, index 0 over here would refer to token ID number 1, and token ID number 1 refers to a specific word, all right, or a token. Index position 1, which is this next one over here, refers to this probability, and that's token ID number 2, etc. So for example, let's assume that the highest probability was 0.1244, which when you multiply that by 100 is 12.44%. So let's assume it was in index position 50,401. Then that index position is a token ID. Then the output token ID in the token dictionary that corresponds to 50,401 would return the token sleeping. And this is called de-tokenization. Then the response would then be the cat is sleeping. And then this reruns steps 2 till 6 to predict every next word. So what it will then do, it'll take this whole input and it'll run it through the transformer again, and it'll then predict the word that comes after that. It'll then take that full sentence, run it through the transformer again, and predict the next word. And that is GPT in a nutshell.